So did you read your book on the chapter on fluid dynamics? So did anybody look at the chapter on fluid dynamics in your book? Come on, there were at least 3 people in the beginning of the semester that were reading the chapters. So there is an opening question in your chapter. And the question is, if you take 2 balloons or more, what happens if you blow in between them? So you just hold them and blow in between. So what will happen? Sorry. So I'm just blowing in between. I'm blowing in between. And I'm not moving them together. What you observe is when I blow in between, they just move together. You can try the same thing with the, yes, your friend is making another demonstration. He is blowing on the top of the paper. He got excited, okay. Yeah, there's another one over here. So the paper goes up when there's somebody blowing on top of it. So you can do 2 sheets. Just take 2 sheets side by side and blow in between. 2. By the way, we also said that in the on Tuesday and in the first hour, if you increase the pressure on one side of a fluid, the gas behaves like a fluid. Okay, so let's see it. Put them vertically. That will be easier. So okay, we have that example. And you see that when he blows on top of the paper moves up. But another example that we said that if you apply a pressure on one side of the fluid, the pressure is transferred to the other side. So just look at this balloon. When I squeeze this part, the other parts gets larger. So I'm increasing the pressure here. That increases the pressure on this part. And well, there's this elastic thing, balloon, which has to expand to balance the pressure. Now let's come back to that example. What happens over there? So we have this air flowing on top of some object, and the same thing happens on the case of the airplanes. You have the air flowing through the wings of the airplanes. Now we will be dealing with the simplest case, the laminar flow. So we just said that if you have laminar flow, if you start with imagine an area. Now the area will be enlarged as the gas or the liquid flows. So it will just become, sure. Well, pushing it into inhaling the air and exhaling the air doesn't really make any difference. Exhaling is easy because then you can just make sure that the air in front of you is moving with some velocity. When you are inhaling, you are just gathering air from all sides. So the air flow will be very small. The crucial thing in that example, or the balloon example, or that example, is that the one part of the air should have a significant velocity. That is the thing that you should do. If we will see now that if a part of the air or a fluid is moving with some velocity, the pressure on that part is lower. So when we have this balloon example, I had these two balloons. When I blew the air in between, the pressure inside reduced, but that caused air and balloons from the two sides to move towards the lower pressure region. We will see now. Well, this is, just imagine there's a flow of air or fluid. Imagine it as a three-dimensional picture. You have a rectangular region on one side. If you would put some floating points on that side, as they flow with the air, they will be distributed over this rectangular region. So that is the initial assumption. That is not the initial assumption, just what's going on over here. This point, the object at this point will become this point will move over here, and so on. Now, as time goes on, we know that there is one part, the liquid in this volume will enter into my region, and the liquid in this volume, okay, so as the fluid is flowing, this area will move to this area, and this area will move to this area over here. So I have this area over here. It will move in, the other area will move a bit out. Now we are assuming that the speeds are not really, forget about the speeds. So what we have over here, on this area we are doing some work. There's the pressure of the fluid here, P1. And there's a pressure of the fluid here, P2. There's some work done on my system, on this block of fluid. I have this block of fluid. As all of the fluid is flowing, this block is also flowing with the fluid. Well, there is a force acting on this block, so there is this force F1. There is this other force F2. Now this other force F2 is pointing in the other direction. This is the force F2. These forces are caused by the pressure in the fluid. There is some work done by this force F1. The work done by the force F1, let's call it W1. This is equal to, now let me call this distance L1. This distance is L2. Just like in the previous case, so this object is flowing, this block is flowing with the liquid. Now the work done by the force 1 is nothing but F1 times L1. Well, they are in the same direction. This is the direction of the flow. F1 and L1 are flowing in the same direction. Well, F1 is nothing but P1 times A1. That is how we define the pressure. The pressure is force over area, so if you multiply the pressure by the area, you obtain the force, times L1. But this is nothing but the work done on area 1 on this side is P1 times V1. Okay, remember this expression. Next week we might be doing some thermodynamics. We will need this one. The work done by this force on my system is the pressure at that point times the change in the volume at that point. Now I can calculate the work done by the force F2. It will be identical. I will have F2, L2. F2 is nothing but P2 times A2 times L2. So I will get almost exactly the same relation with a minus sign. Well, why we have the minus sign? On this part, F1 and the L1, they are in the same direction. On this side, F2 and L2, they are in opposite directions. So that's why we have a minus sign over there. Remember, the work is F dot dl, the vectorial scalar product. So if the force and the displacement are in opposite direction, then the work done is negative. So there is the net work done on my system. Omega total is P1 V1 minus P2 V2. So we know the work done. This is the work done by the pressure. That is the non-conservative forces. But we also know that when we were discussing the potential energy and mechanical energy, we also know that the change in the mechanical energy of a system is the work done by dissipative forces. Well, in that case, we said dissipative forces, but that is any force that we don't write in as a potential energy. So here we can have the gravitational potential energy. That is something we will take into account. So the change in the kinetic plus the potential energy of this block will be given by the work done by the dissipative forces. That is in this case, it will be the work done by the pressure on my system. But we have just calculated the work done by pressure on my system, and we found that it was equal to P1 V1 minus P2 V2. I know the work done. Now let us calculate the change in the mechanical energy. Well, the mechanical energy is the kinetic energy plus the potential energy. So the change in the mechanical energy will be the change in, well, let us first write it in this form. The change in the mechanical energy is mechanical energy. Well, you see, the mechanical energy in this region doesn't really change. There at this, here I always have some mass, which has the some potential energy. It always has the same kinetic energy. So the mechanical energy in this region doesn't change. Well, the mechanical energy, why does it change? Because now some of the mass is, I have some mass over here, and I don't have the mass over here. Now the mass over here contributes a mechanical energy, some positive mechanical energy, because I have mass over there. And the mechanical energy of my system has been reduced over here because I have less mass over there. So the change in the mechanical energy is nothing but the mechanical energy of this part after my system has moved a bit, minus the mechanical energy of the masses over here before the system has moved a bit. And this should be equal to P1 V1 minus P2 V2. Well, this is kind of short question. Well, let's see. The difference between two quantities, each one relating to this part minus that part, is equal to the difference of some other quantities, which is the difference between the property of this one and the other one. Or this just means that, let us write it in this form, mechanical energy at the point 2 plus P2 V2 should be equal to mechanical energy at the point 1 plus P1 V1. Well, I just moved this P2 V2 to the other side and P1 V1 to this side. I didn't do anything else. But you see, this is a property of these points in my fluid, whereas this is a property of these parts in my fluid, and they should be the same. Well, this region is completely arbitrary. I could have taken some square over here or some square over there. So this just tells me that mechanical energy plus the pressure times the volume of my liquid doesn't change as it moves from this point to that point. That is the only thing that is the thing this tells me. So this is what we have. Let me just erase these parts. Now, what I have is, let me write the mechanical energy one. Okay, we said that we have two different parts, the kinetic energy and the potential energy. Now, the kinetic energy is 1 over 2 times V1 squared times the mass of this volume. Well, the mass is nothing but, if the density over there is rho 1 times the volume over there, V1. This is the kinetic energy of the mass in this volume. Well, if I say that this volume is at some height h, then the potential energy of that volume is nothing but rho m, this is the mass, times the gravitational acceleration mg, this is the weight, times the height h1. And this is the potential energy. This is mechanical energy at this point. Mechanical energy of this volume. Well, if you look at here, I have the P1, V1. So the mechanical energy plus PV, well, let me first write this as V1 times 1 over 2 rho 1 V1 squared plus 1 over 2 rho 1 GH1. This is the mechanical energy at the point 1. If we add the P1 V1 to this one, yes, let me show it. So if you just imagine the h is equal to 0 line is over here, this is h is equal to 0, this is h1. So what we have, V1 times 1 over 2 rho 1 V1 squared plus 1 over 2 rho 1 GH1 plus P1. This should be constant throughout the flow. Well, we have been assuming incompressible fluid. And we have been assuming that the mass over here is equal to the mass over here. Now, as your friend pointed out at the end of the last lecture, if we are assuming an incompressible fluid, and if we are assuming the equality of the masses, then we should have the equality of the volumes. So this quantity is equal to the same quantity with V1. The velocity, the V is the volume. Now, this V is the volume. This V is the speed, yes? Yeah, I don't have this 1 over 2 over there. Thank you. Yes? So where would you like to put it? Height is the height of the object. I mean, I just took some reference point. If you like, we can take the reference point over here. It doesn't make any difference. So you see, when we were defining the potential energy, we usually choose the ground to be at zero potential. But you can just set any point as zero potential. Now, this quantity has to be, whatever its value is over here, it should be over here. Now, plus if we have the incompressibility condition, that the volume over here should be equal to the volume over here, this means that the quantity in parentheses, whatever its value is over here, it should have the same value over here. So we have this thing this should be equal to the same thing with 1 replaced with 2. If we add the incompressibility, well, it just tells me that V1 is equal to V2. But this means 1 over 2 rho 1 times V1 squared, this is the speed V1, plus rho 1 GH1 plus the pressure at the point 1. This has to be the same throughout the flow. This is constant as my fluid flows. Whatever the value is over here, it has the same value at the point 1 as its value at the point 2. So let me just remove these ones also. It is the value of this quantity at the beginning of the flow and at the end of the block that I am considering, this is the same. This is what we had shown. This is called the Bernoullis principle. Bernoulli's equation. Okay, so this is a property of the fluid flow that we had derived, but what does that mean? How does it apply to this example? Can you repeat it? Okay, so let's look at this example. So before he blows, what is the pressure on the top and the bottom of the foil? P0. It's the atmospheric pressure, whatever the atmospheric pressure is. Now, then he just increases the velocity of the air at the top. But we know that this is constant. As he blows air, the air, okay, it leaves here, and eventually it will come here. When it comes here, it stops. Its speed is 0. Almost 0, because it's spread out. The pressure here is P0. So at this point we have when V is equal to 0, at this point, almost 0, P is equal to P0. And then in this at this point, at this volume, he is increasing the velocity speed. If there is a larger speed over there than from here, then the pressure over there should be less than the pressure over here. But the pressure over here and the pressure at the bottom part of the air are equal, because the air in the bottom of the paper is not flowing. It's at constant. So if you look at the foil only, the pressure on the top is less than the pressure on the bottom, because the velocity on the top is larger. Well, if the pressure on the top is less than the pressure on the bottom, it tells me that the force per unit area on the top is less than the force per unit area on the bottom. So there is he creates an upward force, an additional upward force which doesn't exist now. At this instant, the system is at rest. Then he creates an upward force. So at this point, the net force per unit area is 0. But then he creates an upward force, an additional upward force. So the air, so the foil, the paper, accelerates in the upward direction. So it's accelerating in the upward direction. So this is just an application of this Bernoulli's principle. The difference in the pressure. The pressure at the top is less than the pressure on the bottom. It is, in a sense, it's like the buoyancy. You see, what causes the buoyancy? The lifting force of the liquid when you immerse something in the liquid. If you put an object, the pressure on the top is less than the pressure on the bottom. So there's a net force acting on this object in the upward direction due to the liquid. Well, there is an upward force, so that force is doing some work, increasing the potential energy. You see, at this point it is at rest. When he fully blows it, it is almost at rest. So the additional work done by the pressure doesn't go into increasing its kinetic energy, it goes into increasing its potential energy. Other questions? Now, your friend's question was, what happens to the potential energy? But you see, the initial velocity and the final velocity of my system is almost the same. So the work done by this pressure difference is equal to the work done by gravity. So the work done by this potential, the pressure difference, goes into increasing the potential energy of the foil, of the paper. Okay, this is one application of this Bernoulli's principle. The same thing holds for airplanes. You see, at this point, you cannot see anything. Well, of course, in this case, there will be two effects. There are two things that you should consider. One, you see, the air here, the layers here are compressed, which means that here, if you just take these four lines, they are spread into some area A1. Here, the same four lines are spread into a smaller area, but that just means that the velocity in here is larger than the velocity of air over here. So at this point, the velocity is larger. That means the pressure is smaller at that point than it is over here. There's a smaller pressure over here than at this point. So just as in the case of the paper example, this pressure difference causes an uplift of the plane. So the pressure difference will be more the faster the plane moves. So that's why the planes need to reach some speed before taking off. Well, here there's another effect though. This is not the only effect that causes the uplift force. Another thing that you should take into account is that if you look at the air over here, the air has some momentum in the leftward sense, in the left direction, the momentum of the air. When the same molecules reach this point, they also have a downward component. So there is some momentum transferred into the air molecules. But that means there's some force being exerted onto the air molecules which have a downward component. But that also means by Newton's third law that whatever is exerting that force, well, the wing is exerting that downward force on the air is exerting an upward force on the wings. So we have these two effects. One is the change in the momentum of the air that is causing it to move upward. The other one is this lifting effect due to the Bernoulli's equation. The velocity is larger over here, the speed of the air is larger over here, so the pressure here is smaller than the pressure over there. So these two effects help to lift the plane as they fly. Is there a question? Okay, so now the same principle also holds here. When the ball takes a curve. Yes. Well, in the case of the planes, the wings are not fixed. The wings, they change their shape. No, not 180 degrees, but the shape of the wings. When you consider the shape of the wings, in this video, the shape of the wings is fixed and it has such a shape. Now, in modern planes, this part can be tilted up or down. So that will mainly modify, that will determine if you are tilting it downward to go parallel, you should tilt it upward if you want to go the other way around. Now it is, you can say it's increasing the velocity by squeezing it in the top part of the wing. So well, in this shape, this is quite symmetrical, so the velocity up, the pressure in the upside and the downside will be equal, but when it goes in this sense, we had seen that the lines are being squeezed at the top than on the bottom. On the bottom, the lines are more or less homogeneous. Well, let me. The lines are squeezed. So here, they are moving faster. Because we had already shown in the beginning of the last lecture is that A1 times V1 is equal to A2 times V2. So if you squeeze a block of air or a liquid to a smaller area, to go through a smaller area, you are increasing the velocity. If you are increasing the velocity, Bernoulli just tells us that you are decreasing the pressure. So on the top part, you are squeezing them, increasing the velocity, decreasing the pressure. Now this is conservation of energy, by the way. We are just applying the conservation of energy to an incompressible fluid. Now, before going to the example of why does the ball curve, let's do another example of the application. Let's just imagine that you have a glass filled with liquid and you create some holes. Let's say one hole over there, another hole over there. And it should be your common experience. So the fluid will flow out of these holes. So which one will go a further away distance? Well, the fluid at the top will just go like this. The fluid at the bottom will go like something like this. Now this the velocity we can calculate using Bernoulli's principle. So to apply Bernoulli's equation, first of all, you need to determine how does the fluid flow, the streamlines, the lines, the particle, the trajectories of the fluid particles as the fluid is flowing. So you can imagine that if the fluid will continue flowing, some water over here, some water particle over here will move down, and it will just get out of that hole. That's a possible trajectory. This is one of our streamlines. Now, if we have such a streamline, Bernoulli's equation tells us that that quantity, 1 over 2 rho v squared plus mgh plus p is equal to constant. This holds through a streamline. So along this line, that quantity is a constant. Now you can just imagine that the hole at the bottom is very small, so the amount of liquid that gets out per unit time is very small, and the area is very large. So you can just imagine that the velocity here, let's call it V1, this is almost zero. The speed of this surface, we can just assume that it is very small and ignore it. So we will have some speed V2 over here. Now the pressure at the top of the surface is nothing but atmospheric pressure. So there we have P0. At the opening, the pressure is again the atmospheric pressure. It is open. So here we also have P0. Well, the density of the liquid, it will be more or less constant. It will not change under the pressures relevant in this problem. So we know that 1 over 2 rho times V1 squared plus, well, but this is not M, this is rho. Rho G H1 plus P0. This is this quantity evaluated at this point along the streamline. This should be equal to 1 over 2 rho V2 squared plus rho GH2 plus P0. This is the same quantity evaluated at this point of the streamline. So we know Bernoulli just tells us that this combination is constant through a given streamline. So here we have the pressure is P0, the H is H1, the V is V1, which is almost 0. So this is almost 0. Here we have the speed V2, height H2, and the pressure P0. Well, this tells you what V2 is. So V2, well, P0, they will cancel each other. This is almost 0. 1 over 2 rho V2 squared is equal to rho G H1 minus H2. So we can just cancel the rows. What is left is V2 square root of 2G, the change in the height. So this tells us the speed. Well, of course, we are ignoring any friction effects. This is just a crude approximation of the speed that the liquid gets out from this hole at the top, at the bottom. And if you remember, if you just release a stone from rest at some height h2, its speed when it reaches the height h1 will be exactly equal to this one. So it is just as if the liquid is making some free fall. This is a simple application of Bernoulli's equation to obtain the speeds over here. Now, once you have the speed, well, this is for a point hole. You can have a large opening. If you have a large opening, you can, the velocity, the speed will be changing from one point to the other point on the opening. But you can calculate how fast the liquid is flowing out. So how long it will take for the whole bottle to drain. So you can also calculate that one, in principle. Any questions on this one? Now let's come to the example of the ball, the table tennis ball or the football. Last thing that we will do, and then you will be free to go. So what we had this table tennis, and there was this ball. And as the guy was hitting the ball, it was giving it an angular velocity. So if you just note how he hit the table tennis ball, as the ball left that side, it was rotating in the counterclockwise sense. So it had some angular velocity vector pointing upwards. And the trajectory of the ball was Initially it was moving in this direction, and then it came here. It hit at this point. This was the trajectory of the ball as it was moving. So this is what's happening. So this is what we observed. Why? It is? Okay, I just want to give you this additional information. If he did the same thing in vacuum without air around it, it will go through a straight line. So just because it is rotating will not cause it to change its trajectory. It will not curve with only rotating. Rotating plus the air around causes it to rotate, to curve. So you see, if you look at the relative velocity of the surface and the air, you see, the ball is rotating like this, so the relative velocity of air with respect to this point is larger than the relative velocity of the air with respect to this point on this side. So the velocity here is larger than this one, so the pressure on this side is smaller than this one, so it should move in this direction. So it should bend like this. Oops. Didn't you say that the relative velocity here is larger than the relative velocity over there? So the pressure over here is less than the pressure over here. So the force in this direction is larger than the force in this direction. So it should curve in that direction. But it curves in the other direction. No. Yes. In vacuum. Yes. We are sure. Well, let's see. He hit the ball. After he hit the ball, this will be his trajectory. Let's ignore what happens when he hit the ball. The initial condition is that the ball is moving in this direction with an angular velocity given in that direction. After that motion, throughout this motion, it will bend like this. So it's just like, if you hit the football like this, the football is over here. If you give it a spin in this direction, you know that it will rotate like this. No? Why? The same is holds for the top part too, no? Okay, something for you to think over the next week. So you are saying that it is due to friction, it causes the air on this side to move faster, you mean? So as it is rotating like this, the air in the reference frame of the table you mean, on the reference frame of the table, it is causing the air molecules on the left to move faster than the air molecules on the right. Is that what you mean? Well, that is the answer, by the way. Well, as it is moving, how many of you smoke? Okay, so you shouldn't smoke. But that you are smoking, make an experiment. The next time you smoke, go close to a wall and exhale the smoke very slowly so that it will have zero initial velocity, initial speed, almost. Do it very close to the wall so that the smoke will be adjacent to the wall, and do it in open air away from the wall and see what happens. Do you smoke? Did you try it? Well, you will see that what you will see is that the smoke will just stick to the wall and it will not disperse around. That is because when objects move, they create a very thin layer around them that is at rest. So they are dragging, the terminology is that they drag the gas and the fluid around them. So that is what causes this effect. Without that drag, this wouldn't happen. So with half of you, see you on Saturday. With the other half, see you on Tuesday.